Hello, my name is Joksimovic Miodrag, and I am a part of 8 Bridges team of students from the School of Electrical Engineering, University of Belgrade. We are taking part in the 2019 International Future Energy Challenge, and I'm going to present a model we made for Typhoon Hill to simulate the properties of our device. For this competition, we are making an e-drive for a bicycle. The design process is based on the requirements for the power density and temperature rise of the device. In this intensive design process, the Typhoon hardware and Typhoon's virtual hill have proven to be quite useful. Here you can see the basic topology of the drive, which will be thoroughly explained later on. The beauty of the Typhoon's software is that we can test and simulate the explicit code that will be used on the real DSP later on. That's the reason why we used Typhoon C function blocks to implement our control instead of using Simulink-like blocks. The model we are using for simulations consists of the lead-acid battery with a nominal voltage of 48 volts, DC-link capacitor seen right here, 6 transistors, 2 for each leg of the inverter, and the motor. The motor is a permanent magnet synchronous machine with 4 pairs and an encoder coupled to the shaft. The position of the rotor is used for the regulation purposes after some corrections, while those others are just used for the purposes actually to be seen on SCADA. We are also measuring the currents in each phase, and after oversampling and some rate transitions, because the oversampling block runs 32 times faster than the regulation blocks, those currents are going to the ABC to alpha beta block and to alpha beta to direct quadrature block. Now we have measured the currents in the direct quadrature system, and those currents are in the current regulator block. The current regulator takes on all these variables as inputs: the position of the system, the references from SCADA input, measured currents in the direct quadrature system, and takes the signal of error, and after some regulation, which is given right here, right, gives the voltages in the DQ system to be later on used by the space vector modulation block. Those voltages are transferred to the alpha beta to the ABC system right here, and the space vector modulation block takes the minimal of all three, sums up with the inputs, and gives out the duty cycle references to be used as a control for the transistors. Let's now move on to the SCADA system. Here we can see some gauges which are measuring and showing the battery voltage, shaft output power, the angular velocity of the shaft, and the electrical currents, voltages, and so on. Over here we can see some sliders that are used as the references for the torque, current at the Q axis, and the current at the D axis reference, and there's measurements. Here is the slider for the load and phase, and measurement of the phase currents of the motor. Here we can choose the state of the drive. It can be in the normal operation or as default operation. If the fault is selected, then the switches over here are closed, and they simulate the short circuit of the motor. Now let's run the simulation, force a trigger, and wait for for half a second. We can see the currents, the phase currents, direct quadrature currents, and the torque, which is this blue line over here. Let's force a trigger once again. We can also see, well, it's a bit too fast. Let's slow down. Let's force a trigger once again. Over here we can see the phase voltages, phase reference voltages, and the duty cycles of the transistors. They have this characteristic space vector shape. Alright. Here is the measurement of the currents, and the values that can be measured on the scope are there are a lot of them. There is the battery voltage, duty cycles, some currents in the ABC, alpha, beta, DQ system. There is electrical torque, mechanical angle, and so on and so on. Output power, theta of the shaft, also the theta of the DQ system, and so on. Alright, I hope you liked my presentation, and I hope that we can get a Typhoon Hill. Goodbye.